Hi, myself is Kunal Padmani, and today I'm talking about the 3D NAND technology.
Hello friends,
So
myself
basically,
is
we are
Kunal
talking about
Padmani
how 3D NAND
and today I'm
technology
talking
is
about 3D
working
NAND
in the
technology.
real field and how it's built
So my
with
topic is
the
3D
NAND
NAND
technology.
technology.
How does it work in real field? Because this year, actually the last year, Samsung announces 3D VNAND technology, which they going to be used in Samsung solid state drive. So 3D is like a three-dimensional NAND technology. So how they going to use like three-dimensional flash memory is emerging to fulfill the ever-increasing demand of storage capacity. In 3D flash memory, multiple layers are stacked to increase bit density and reduce bit cost of flash memory. However, the physical architecture of 3D flash memory leads to a higher probability of disturbance to adjacent physical pages and greatly increased bit error rates. So, the NAND flash business is transitioning from process that has been used for the past 20 odd years, and let's call it 2D technology. And the new process that promised to carry the technology through the end of the decade, and it's a 3D NAND technology. So there is some trouble with the 3D NAND technology. So what is the trouble with the 3D NAND technology? Like 3D NAND is seriously tough to manufacture. This is clear from the fact that Samsung announced mass production of its VNAND generation of 3D NAND last August. So what's so tough about 3D NAND technology? The suffice it to say that 3D involves processes that have never been before put into production in any kind of semiconductor, and that automatically means that the road of 3D will be extraordinarily challenging. So the second one is how flash memory works. Actually, the first point is like how flash memory works. So I'm going to give you an overview of the how flash memory going to be work in the real world. In flash memory, a floating gate, you can see right here a floating gate. So the floating gate is a CMOS based transistor that is capable of holding an electrical charge. So basically, flash memory is a type of electronically erasable programmable read-only memory, or you can say that EEPROM chip, which is programmed and erased in large blocks. So the chip cells are arranged in a grid that has two transistors at each intersection. So one of the transistor is known as a floating gate, and which one is here, the floating gate, and the another one is called a control gate. So you can see the control gate, the upper one is a control gate and the lower one is a floating gate. So the two transistors are separate from each other by a thin dielectric material generally referred to as the oxide layer. So you can see here a oxide layer, there is a two oxide layer, and which can be separate to control gate. Because the floating gate is electrically isolated by the oxide layer, and any electron placed on it are trapped there, and this is what makes flash memory non-volatile. So flash memory work by adding or removing electrons to and from a floating gate. A bit 0 or 1 state depends upon whether or not the floating gate is charged or uncharged. Where electrons are present on the floating gate, current can't flow through the transistor and the bit state is 0. So this is the normal state for a floating gate. When electrons are removed from the floating gate, current is allowed to flow the bit state 1. So this is basically overview of the how flash memory going to be works. So how they going to use the two transistor and how the floating gate and control gate like separate from each other. So this is the basic of the how flash memory works. The second one is like NAND versus NOR. Why they using NAND compared to NOR? So there is some, like I capture one image from the web which shows the NAND versus NOR, but I will illustrate in detail. Like flash memory has become powerful and cost effective solid state storage technology, which one widely used in mobile electronic device and other consumer applications. So two major form of flash memory like NAND flash and NOR flash have emerged as the dominant variant of non-volatile semiconductor memory utilized in portable electronic device. So NAND flash, NAND flash, which was designed with a very small cell size, like cell size we are talking about it later in my video. So like NAND flash, which was designed with a very small cell size to enable a low cost per bit of stored data, which one or maybe has been used primarily or as a high density data storage medium for consumer devices such as the digital still cameras or USB solid state drives. And NOR flash as a typically been used for code storage and direct execution in portable electronic devices such as cellular phone and PDS. So you got a basic like basically where they're going to be used NAND and where they're going to be used NOR technology. So recently, however, the distinction between the two types of flash memory has become less clear. New cell phone controllers that support NAND flash as an alternative to or addition to a NOR flash have been helped make a NAND viable alternative for a broader array of applications. In addition, data storage capacity and performance requirement in cell phone have increased significantly with the growth of feature-rich phones that incorporate with camera, music, video, gaming, and other functionalities. So you got overview like why they're going to be use NAND technology in mobile. NAND flash has become an attractive alternative for the data storage aspect of today's cell phone because of its high speed write and erase performance as well as its low cost per bit. As a result, designers of memory subsystem in portable electronics are now using NAND in some traditional NOR based application. So for today's full feature cell phone, many designers are utilizing memory architecture that combine NOR with NAND for data storage, or they are using NAND as the primary flash memory in combination with the low power DRAM, in which the program code can be shadow and run. So like in either case, the different type of memory are frequently stacked in multiple chip package to create a single component. And this figure provide a summary of how NAND and NOR flash vary for a number of important design characteristics like capacity, read speed, write speed, active and standby power consumption, cost per bit, ease of use for file storage and code storage application. So you can see now this blue line is for a NAND gate technology and this green line for the NOR gate technology. So you can see that, like, let's start from here. Okay, hold on. Let's start from the cost per bit. Like in cost per bit, you can see that it is a low cost per bit. Like first, I can say that like NAND has a low cost per bit, easy file storage use, high capacity, high write speed, and medium read speed or low active power, and it has a medium standby power, or it has the main thing, it has a hardcore execution. And compared to that, NOR has a low standby power, high read speed, and easy core execution, but it has like some you can see that it has a high active power. Yeah, it's a high active power, and it has a high cost per bit, and also it has a high file storage use, and even it has a low capacity. So you got a like basic overview why they going to be using NAND technology compared to NOR. And here I can show you like NAND and NOR flash memory architecture. You can see on the left side NOR flash architecture, and here is a NAND flash architecture. Like in the internal circuit configuration of a NOR flash, right here, the individual memory cells are connected in parallel, which enables the device to achieve random access. This configuration enables the short read time required for the random access of microprocessor instruction. So NAND flash is ideal for a low density, high speed read application, which are mostly read only, often referred to as a code storage application. Yeah, you can say that. And for the NAND flash architecture, NAND flash was developed as an alternative optimized for a high density data storage, so giving up a random access capability in a trade-off to achieve a smaller cell size, which translates to a smaller chip size. Like you can say that a smaller chip size and lower cost per bit. This was achieved by creating an array of 8 memory transistors connected in a series. So it's like if you connect 8 memory transistor connected in series, is basically a NAND flash technology. Utilizing the NAND flash architecture, high storage density and smaller cell size, so NAND flash system enable faster write and erase by programming blocks of data. So NAND flash is ideal for a low cost, high density, high speed program erase application, often referred to as a data storage application. Yeah. And the next thing is like you guys, I'm talking about what is 3D NAND. So basically here I am giving you what is the 3D NAND, exactly how they convert from the planar NAND to a 3D NAND. So NAND flash cannot be scaled much further in a length and width on the die surface. So like Toshiba invented a 3D NAND flash has been adopted and refined by all flash makers, and the idea is simple. Rather than shrink the cell length and width, like here you can see shrink like length and the width, why not turn the NAND string to so that the standing on its the end, like here you can see that. See, so this concept is illustrated by the one of the website which I taking this, like how the what is the 3D NAND technology, and like which was provided by Applied Materials. So in a standard NAND string that normally runs longitudinally is a turn on its end to become a vertical string. Not only that, but it makes things easier if the string is split into two sections and form into a U-shape rather than a single column. So you can see that here is a typical planar NAND cell string. You just stretch out it on the middle and just fold it over and just stand it vertically, and you get a future 3D NAND technology. So naturally this can be done by manufacturing NAND string and folding them. So this concept is basically instead the string is formed vertically using a completely different manufacturing process than is used for standard NAND flash. In fact, this is a technique that is new to all semiconductors. So if you can lay down a horizontal series of control gates, then run a vertical series of floating gates and channel that respond to those gates, then you can build a string that may be several cells long in the same area as a single planar cell. So this is the basic what is the 3D NAND technology. And another thing is like history of Samsung NAND flash, how they like how they year by year increasing the width size between the cells. Here you can see that in 1999 there is a 120 nanometer and it says only 1 GB. So like year by year they increasing the size, like keep the technology leadership through the continuous scaling, we can say that. So it's a worldwide #1 market share in NAND flash since 2002. So it's scaling is getting difficult for them, but like need a technical breakthrough to continue after like sub 1 YNM, which was like 128 GB going to be stored. Like so 1 YNM is around 15 nanometers. So it's like 1x 1y 1z, it's like end of the alphabet, and 1x is for like around 19 nanometer, like will be in full swing was in last 2012, and 1y is around 15 nanometer, which was developed by 2013, and 1z likely the last generation of NAND. I do not have any idea what is the exact length of it, like how many, maybe 4 nanometer, I think so, because one of my professors said that it's going to be a 4 nanometer, so I'm not sure. So here is the sorry, this is the history of the Samsung NAND flash technology. Okay, so here is the floating gate technology, like how the floating gate improve year by year, like not year by year, like you can see here on the left side there is a number of electrons, and here is the design rule. So like design rule in 120 nanometer there is a more error threshold, and the storing is a 1 word data, and like after this decreasing the length between the gates, you can see that on the, like if you are going left to the right, there is a low error threshold, and the storing voltage data is going to be decreased. So it's like 19 nanometer to 1x, and there is some technology limitation, like after what is an M, I don't know what's going to after that. So maybe I don't know, but they can they are going to figure it out what they are going to use in the future. So here is a 3D vertical gate, like how 3D VNAND structure innovation. So like you can see a charge trap, like a what is a basically charge trap, right? So what I can say that a charge trap was a means of doubling the bit capacity of its products. So you can see the charge trap. So it's like a simple meaning, it's a doubling the bit capacity of its product, and it was an inexpensive alternative to standard MLC flash. To date, these strategies work very well. Like, I don't know, but they said it's work very well. So maybe. So 3D NAND uses a charge tray because it's extremely difficult to create features like floating gate, sideways lithography work from the top down. A charge tray when used to replace a floating gate doesn't need to be patterned. Since the charge on one bit, its charge tray will not leak through the insulating charge tray player into the adjacent bit cell. So there are other benefits to using a charge tray though. Like charge trays requires a lower programming voltage than do floating gates. So this is turn reduce the stress on the tunnel oxide. Since like stress cause wear in flash memory, the lower programming voltage gives a charge tray flash greater endurance than conventional floating gate. A charge trap can improve a bit like bit reliability another way, like since the charge trap is in insulator, the charge in the trap can't flow from one side of the trap to the other the way it would in the floating gate. Like at the flash memory summit, Samsung likes this to using a cheese instead of water for the charge trap. Like what they said in the summit, like they're using the cheese instead of the water. Although the stress induce a leakage can drain and the charge of a floating gate, the same phenomenon would only drain the charge of a portion of a charge tray without disturbing the charge on the remainder of the tray. So this makes it far less likely that a single point defect in a tunnel oxide layer would cause a bit to fall as it would in conventional floating gate flash. You can see that here, right? There's using charge tray flash and the control gate instead of the floating gate, and yeah, you can see that. So like reduce oxide stress and lower sensitivity to single point defect combined to significantly improve overall reliability. Samsung in its VNAND rollout last August claimed that a charge tray provides twice to 10 times the reliability of sub 20 nanometer planar floating gate NAND flash memory. Also, charge trays consume less energy during program and erase, so a 3D NAND that is based upon a charge tray is likely to be more energy efficient than its floating gate counterpart. This translates to longer battery life. Like Samsung says, its a VNAND provide a 40% improvement. It says a 40% improvement in power consumption over planar flash. So it's like too big. It's like you can say 40% your power consumption. It's a big deal for the. It's a big deal for in future, like 40%. Oh wow. Okay, so charge trays are also faster to program than conventional floating gate flash. Samsung claimed that its a 3D NAND charge tray support twice the write performance of a sub 20 nanometer planar flowing gate NAND flash memory. Although a subsequent release said that the sequential and a random write speed of a VNAND based SSD increased only 20%. All in all, like chart trapping is a good technology, and it's something of a surprise that it hasn't found more widespread user and planar flash design. So here you can see the 3D vertical gate, like it's overview. Like 1971 they're using floating gate, and after that they're using chart trap flash technology, and on the last year they find out the 3D vertical NAND technology. So it's very cool innovation. So here is a VNAND cell. You can see that the word line right here and the bit line. So you don't have to connect your word line anymore. Like it's a, you can say that cell to cell interference between bit line and word line interference are totally free. Like word line interference, this word line interference almost free, and this bit line interference is free. And patterning, it's like you can you are free from the patterning issue from the. So those this is the basically a VNAND cell, which was I'm talking about earlier. So this is the pattern of the VNAND cell, and this one is they're going to use in the 3D NAND technology. So this we already did that, I think so. Oh, yeah. So the benefit of charge traps over floating gates, that's what we talking about just before that, like how charge traps are going to be benefits for over the floating gates. So here is the how do you access the control gates. So here is the thing is like there you can see the three image on the left side. here is like a basic view of the 3D technology. So, and I'm talking about in this slide I'm talking about how do you access the control gates. So one of the thornier problems in making 3D NAND is the job of connecting the peripheral logic to all those control gates that are on layers buried somewhere within the bit array. So remember that the control gates are conductive sheets of polysilicon or tantalum nitride at a various depth in the chip. The problem boils down to this, like you can't run connection from each layer up or down side of the chip to get the CMOS circuit below. Instead of, you have to create a terrace structure to expose and connect to each layer. So those connections are made by etching a stair step pattern. You can see here a stair step pattern. So yeah, so the I said that this connection are made by etching a stair step pattern into the layers and sinking wires down to connect with each layer. This illustrated in this in this one, like in Samsung TCAT, like you can TCAT or TCAT 3D NAND. So state steps are difficult to manufacture, you know. So like I will explain this process in some depth in this slide, like how you are going to manufacture the state steps in your lithography using lithography. So after all, no chip today uses state step each. So it's a totally new process that had to be developed for a 3D NAND technology. So this etching must be precisely controlled because each wire must align precisely with its polysilicon layer, and this is a huge challenge, you know. Yeah. So here I'm going to show you how they're going to like manufacture control gates, or like you can say the 3D NAND technology. What is the basic of 3D NAND technology? Like on in the top left right here on layered context, you can see, right, on the top left side we see stair steps that are improperly connected to their wires. Like in the top circle connection right here, the wire only halfway connects to the steps, since steps were each with an uneven width. So this is explained by the top middle photos. Like see here, in uneven steps, you can see that if steps are uneven, then the wire connection to the word line will have inconsistent resistance, leading to unreliable performance. Like which was like if you have inconsistent resistance, then it will be leading to unreliable performance. The photo at the right shows the taper edge on the steps. Yeah, so you can see here taper profile. Yeah. So here though the which I can say, like which leads the problem dissipated dissipated in the lower red circle on the top left drawing. Here the wire may or may not actually connect to the word line, leading to the prospective failure on our entire flash block. So the lower three frames of this photo shows the ideal, like steps are evenly attached and profiles are straight. See, attached and profiles are straight, leading to a reliable connection. So one fortunate thing about the etch process is that like layer can be specifically etched through the various means, like etch chemistry and the color of radiated light, and the etcher can, well, whether it is etching one material or the other, and can be stopped as soon as it's reach a new material. In the BICS like case, state step must stop etching when it reaches the polysilicon word line plane. For TCAT, etching would be stop once it reaches a tantalum nitride plane. So either way, the process can be stopped at each layer very precisely. Now we could each portion of the state step, then perform a lithography step, then each another, and so on. But this would create a like ballooning number of lithography steps. Like while a typical NAND flash today might require about 35 mask steps. So yeah, you got that right. It's a 35 mask step, and 64 layer state step would require 64 mask step in addition to the 20 or more mask step used to build an underlying CMOS control logic. So the connector at the bottom of the two stack, like U and the columns themselves, for this region, for this reason, lithographic approach would be a prohibitively expensive. So keep in mind that the whole point of moving to a new process is to reduce cost. So like instead of process was developed in which lithography is used once a pattern mask, and that mask is repeatedly used and etched to create the step pattern. The third graphic show how they are going to like use the etch and how they use the mask here. So the first the mask is photographically patterned and etched to create a whole the width of single step, like step in a graphic. You can see a step here, like from mask is to poly, pull back, h to next poly. So like on the first step, poly layer is each on the like each to poly. I use a faded color to show what was just each away. In step C, the hard mask is each sideways. You can see that, which I have been told is very controllable in the width of the single step, and this is called a pullback and has been put into production for other process. So it's a well understood approach. Again, layers are attached to the start of a new polysilicon layer, and this is the step D here. But the part that has already been etched goes down another layer, while the newly exposed portion is down to the first poly layer. So this process is repeated according to the number of layers there are. So in the case of Samsung Nand with its 24 layer, these steps would ideally be repeated 23 times. Yeah. Existing production like volume semiconductor process use of pullback no more than once. Like controlling 23 pullbacks can be problematic if it's not well controlled, since error can accumulate. Yeah. So today manufacturer will perform this process only 6 to 12 times before using a second photolithography step to create a new mask. As confidence grows, the number of pullbacks per lithography step will increase, with the ultimate goal of forming all of the steps using only one lithography cycle. Finally, a very thick silicon dioxide layer is deposited on the top of the entire staircase, and another pattern is lithographically created for the wires, and the trends are etched down to the polysilicon layer. So the etch is controlled to remove only the silicon dioxide, so each trend stops when the polysilicon is reached. The wires are then filled with the conductive material, tungsten or polysilicon, to bring the control gates connection or word lines to the top of the chip, where it can be routed to other wires that connect them back down to the CMOS logic on the substrate that drive the array. The step etch is yet another very difficult and new process that must be managed to successfully mass produce 3D NAND. The wire must land precisely on the designated step and not on any other, or the word line will be sorted to each other. If the wire doesn't make a solid connection with the poly layer, its resistance may prevent that entire world from working properly. This means that the mask pullback must align precisely with the litho pattern of connecting wires. You can imagine what a challenge this is like. What is striking is that the process of getting to the word line reverses the complexity of making the vertical bits themselves. Clearly, 3D NAND involves a broad range of challenges, and it will take a significant effort to move from planar process to a 3D. So, like, why do we need 3D NAND? Like this era, we want fast. Like we want everything faster. So, like everyone want to know about why do we need 3D NAND technology. Like a memory chip of a certain area costs about the same amount to produce, so no matter how many bits it holds. Naturally, the more bits you can cram onto this chip, the cheaper the price per bit will be. Low cost is the utmost importance in the world of memory. So like memory chip makers have shrunk the cost of bit some 9 orders to magnitude since the 1960s, largely by shrinking the process of scaling or scaling to increasingly tighter process geometries. Like flash has always has been expected to reach scaling limit. Like over the past few new generation technologists have developed a new process and have harnessed innovative material to push scaling faster than that it has gone before. But today we are approaching the point at which planar NAND just cannot any longer be strung. So the technology has progressed from the standard floating gate to a cap structure. Like picture in, you can see here the cap structure. Like this one is a control gate and the floating gate. which we already talked about before. So like this technology has progressed from the standard floating gate to a capped structure, since the constant shrink have caused the undesirable capacitive coupling between the floating gates and adjacent cell. So right here, floating gate and adjacent cell, to reveal the desirable coupling between the control gates and the floating gates. Yeah. So the cap well developed to solve this problem, but cap cells can only be shrunk to about 20 nanometers, since the capping material limits how closely floating gates can be placed to one another. So to get past this, some manufacturers have replaced the silicon based gate dielectric with the high K material that allows the two gates to be placed closer to each other while still maintaining a high enough desirable capacitance to the trick. And so the like benefit of Samsung VNAND over 2D planar NAND, like it's a it has a more capacity, more speed, more endurance, and more power efficiency. So like Samsung's new 3D VNAND will be used for a wide range of consumer electronics and enterprise applications, including like solid state drives, and consumer can expect their handheld computers to perform better for longer periods of time between charges. The data center manager can expect increased productivity and longevity while saving on their power bills. So this is the main overview of the Samsung 3D VNAND technology. Thank you for listening. Thank you so much. Bye.